Three more things that we need to understand or think about in the velocity field before we can get into how the forces affect fluid flow. And to remind you, at each moment in time, we can picture an imaginary grid of squares of fluid parcels in any velocity field. That's the Eulerian perspective, and we can consider and have considered the velocity and the acceleration of each one of those squares. That's the velocity and acceleration field. And at each moment, you could then redraw the squares and redo it, and that's the idea of thinking in a Cartesian coordinate system about a velocity field. We're still going to stick with a Cartesian coordinate system right now, but we need to think about three things more than just the velocity and acceleration field. So we also need to consider the volumetric strain. This relates to conservation of mass and conservation of volume in a flow. It also relates to the effects of pressure stresses and momentum. We also need to consider shear strain. This relates to viscous and frictional stresses, especially in boundary layers, everywhere in the flow, but especially present in boundary layers. And also vorticity. Vorticity is another way to look at fluid flows. It's the spinniness of sections of the flow or the swirl. It has to do with smoke rings, vortices. It also plays a role in boundary layers, although it's harder to see there. It's definitely there, but it's just a little bit harder to wrap your head around how when you first see it. This video shows all three of them. So this is the same converging channel as before. I'm going to pause it for just 1 second. But instead of marking single points with fluid parcels, we are marking all of them in that sort of grid there. And you can see that from left to right, any given square gets stretched out. So that's to do with the volumetric strain, the stretching and squeezing. You can see that they're getting sheared. If you've got a deck of cards and you shear it like this, you end up with that sort of parallelogram shape. And you can see that all of them, in addition to getting stretched and squeezed, are also getting sheared. And the vorticity is also present, especially in that boundary layer, the regions along the top wall and along the bottom wall, where you see that sort of distortion that is not just a stretch or a shear. It's the fact that there is some twist or some distortion right there near the boundary, but not farther from the boundary. So you can see it in all three of these. Spend the time thinking about the volumetric strain and the shear strain in there. It's harder to see the vorticity. We're going to talk about all three in the next couple of slides, next 3 slides. So, volumetric strain rate. Volumetric strain rate is to do with how each fluid parcel stretches or squeezes. So it's very much rectilinear motions that wouldn't distort the shape of the square from a rectangular shape. Wouldn't turn it into a parallelogram, for example. It would keep the angles at right angles. And an example of this is as close as the nearest tap in your kitchen or your bathroom, outside at the hose, wherever. This picture here is just a simple steady laminar flow from a tap, and there's a diagram to the left of it. And what you can see in both is that as the flow comes down, it necks down to a smaller diameter. It has one diameter at the top up here, and it has a smaller diameter at the bottom, or near the bottom down here. And we've shown that schematically, where this dimension is larger than that dimension. And this has to do with volumetric strain. So volumetric strain rate is the rate of change of the volume per unit volume. So its hard and fast definition is 1 over V di V di T, or dV dt rather. And if we think about a simple square element, which is some delta x by delta y in dimension, then that small volume element, thinking in just 2D, the volume is delta x by delta y, and the rate of change of volume with respect to time would be therefore d delta x delta y dt. Let's throw some coordinates on here. This is the x-axis, which is also u velocities. This is the y-axis, which is also v velocities. And we can just do the product rule here. We've got d by dt of a function. So let's just expand that out. The denominator, 1 over delta x delta y, stays the same. We've just done the product rule and pulled out delta y d delta x dt plus delta x d delta y dt. And that's okay, so that's just basic calculus. But now, how do we express that d delta x dt? How do we talk about the change, the time rate of change of the x dimension of this square, or of the y dimension of this square, with respect to time? Well, if we consider a reference frame that moves with the bottom left corner of this, so let's fix our reference frame to this corner. Then if we're traveling with that bottom left point of this fluid parcel, then the left face is going to move with some velocity u, and the right face is going to move with some velocity u plus the partial of u with respect to x times the delta x. So if we're moving with that reference, moving with that bottom left point, then what we see is that the right hand side moves as di u by di x times delta x. So the rate of change of u with respect to x times the change in x. Likewise, the top face, if we're moving with the bottom left corner, that means we're moving with the bottom face as well, but the top face is going to move at some different velocity, which is v plus di v by di y times delta y. And again, if we're moving and with that bottom face, then we lose the v velocity on the bottom just because of the reference frame. And what we're left with is di v by di y times delta y. That is the that times delta t is going to be the amount that the left or the right hand face moves to over some period of time delta t. So here's t, and here's t plus delta t. And over that small delta t, the shape of this square has changed by di u by di x delta t, and by di v by di y delta x delta t. So we can substitute this in, and if we substitute this in and do a little bit of rearranging, then we come up with what's shown here, and we can cancel out the denominator because we've got a delta x and a delta y, and a delta x and a delta y. And so what we're left with is that the volumetric rate of strain is just di u by di x plus di v by di y. And I want to pause for a second here and introduce one last topic, or one last concept about this. We're talking about the rate of change of volume per unit volume. If you think about that, that's squeezing something or expanding something. Excuse me. Fluid elements have a fixed mass. Fluid parcels have a fixed mass, so the mass is not changing, but the volume is. That means we're talking about a change in density. So it's 1 over density times the material derivative of density, just like we had material derivative of velocity before. And so what we're saying is that for this simple 2D case, 1 over density times the rate of change of density with respect to time is di u by di x plus di v by di y. In this course, in 351, we will be dealing with incompressible flows. That is to say that the change of density due to pressures is minuscule. This is true for liquids. It is true for gases in the types of flows that we're considering. And as a result, in that case, di u by di x plus di v by di y is equal to 0. there is no change in the total volume of a fluid element over time. We can also look at how much each fluid parcel shears or slides relative to relative to each other. So in this video here, you see that in that those initially square marked areas, not only do they get elongated out, but they also get sheared. So if you think of making a rectangular shape with both hands, it's not just that it's changing like this, it's also shearing it, that you're bringing your thumb and forefinger together. It's changing from a rectangular shape into a parallelogram. And so that is to do with the shear strain rate. So the shear strain rate is the rate of change of that angle, of that initial 90-degree angle in that initially square fluid parcel. So it's the rate of change of the angle. If you take a look at this schematic, it's the rate of change of beta and alpha. A little bit of math here. So small angle approximation, beta and alpha can both be related to eta and xi. Specifically, beta is going to be xi by y. And now if we do a little bit of calculus, well, we can relate what xi is to di u by di y. So we have some gradient in the u velocity with respect to y. So maybe it's 0 down here and higher up top. So there is a change in the u horizontal velocity with y, the vertical position, and di u by di y is that slope. Di u by di y times delta y is the amount of change from one side to the other. And if you think about it, multiply that through by delta t, you get a distance that that top left edge has traveled. Specifically, it's traveled by delta xi. We can do the exact same thing with alpha and eta. So alpha is eta by x. Eta is di v by di x times delta x. So we could likewise have a slope in velocities. And we're talking about small delta t's and small parcels and small dimensions all the way through here. So I'm exaggerating everything out. But you can certainly approximate that di v by di x to be linear, in which case it's going to be or that change as a simple linear di v by di x, in which case, as I've drawn, it's going to be something as simple as that. And then that di v by di x times delta x gives you a difference in velocity from the bottom left to the bottom right corners. And that multiplied by delta t gives you a displacement from the bottom left to the bottom right. And so that calculus in there is what we need, and that small angle approximation lets us then put everything together and find that that rate of change of angle, that shear strain rate, is just di u by di y plus di v by di x. Wherever we have a large value of shear strain rate, we have a lot of shear stress. There's no way that you can get that shearing motion from squeezes. You have to get them from shears. Again, think about a deck of cards. Take it. If you push it, it will, well, since it's a solid, it will either not move or buckle. But the only way you're going to get it to shear and take on that parallelogram shape is if you shear the top and the bottom of the deck of cards. Also, near walls, the inertia of the wall slows down the fluid, or makes the fluid take the same velocity as the wall. We call this the no-slip condition, and we can see that in the video that we've got here. In the top left and the bottom left, basically at the inlet of this channel, you can see that the velocity near the wall is being slowed down greatly, and the velocity a little ways away from the wall isn't affected. As a result, you have a really large di u by di y, and it's much, much larger than di v by di x on the far left side of that inlet, or of that video at the inlet at the wall specifically. So very often you're going to have the case where the shear strain rate is predominantly taken over by one of either di-u by di-x or di-v by di-y, depending upon, sorry, di-u by di-y or di-v by di-x, depending upon what orientation you're talking about. And obviously you could write this for x and z or y and z as well. You could write it for any two coordinates in free space. The last way to think about the velocity field is to not think about it as velocity at all. Instead, to think about it as vorticity, which is how much each fluid parcel spins or turns or curls or rotates. And specifically, in a vector calculus sense, it is literally the curl of the velocity field. Vorticity is 1/2 the rate of spin. It is 1/2 the curl of the velocity field, often denoted as omega. In the text, they use this other symbol just to keep you from being confused with the W component of velocity. Vorticity is spin. The most quintessential example of it is a vortex ring or a smoke ring. There's tons of videos out there. One of my favorite is of these dolphins playing with vortex rings. They flap their flipper in a certain way to create a vortex ring. They inject some air bubbles from their blowhole and then they play with them. You can see that they can split them, they can grow them, they can stretch them out, they can shrink them down. You can do all sorts of really interesting things with vortex rings. You can think about fluids really productively by thinking of it in terms of vorticity because of some of the rules about how the stretching and compressing happens. It's all about angular momentum, so when you stretch it out, the amount of the velocity of the spin increases, but you have conservation of angular momentum. That tells you other things. If you get into advanced fluid mechanics, you will learn a lot about vorticity. You will do a lot with it. Right now, let's just introduce it. To remind you, the curl is the same as the gradient crossed with the velocity field. Further, if you want to think about that in a very simple sense for a three-dimensional space, it is the same as the determinant of this 3x3 matrix. So to take the component in the k direction, which would be the xy plane curl, so the curl in this xy plane points in the k direction. Everything that you learned about angular momentum applies here. That k direction of vorticity you would determine by crossing out the rest of the row and column and taking di-v by di-x minus di-u by di-y. And if we think about this, well, and that is indeed what it is, 1/2 di-v by di-x minus di-u by di-y. That's omega xy, omega xy, there you go. And if we think about this in terms of the diagram, similar to what we've drawn for shear and for volumetric strain, we can draw a really similar diagram, and it's going to look really similar to the shear case, but here, instead of the velocity gradients tending to shear the fluid parcel into a parallelogram shape, these velocity profiles, or these slopes of di-u by di-y and di-v by di-x, are going to tend to rotate that fluid element. Specifically, they're going to tend to rotate, when omega is positive, it's going to tend to rotate in the counterclockwise direction. So as I said, vorticity allows you to do all sorts of really interesting things in understanding how fluids flow and predicting how they're going to behave. You can stretch and compress and bend vortex lines. There's rules about how vortex lines can't terminate in a fluid. Vorticity diffuses over time, and so you can think about fluid flows as a diffusive problem rather than as a inertial problem when you're thinking in vorticity. And vortex lines also can be thought of as inducing flow in other parts of the field, which leads to these self-traveling vortex rings. Yeah, so it's a really interesting way to think about fluids. It's not going to be in our course a lot, but it is something that you should know this level about. So to sum